Last time we stopped in the middle of analyzing the ISO data algorithm. And the idea of this was to segment an image into two parts. So we were thinking about handwriting in front of a constant background, and we wanted to do thresholding to separate the handwriting from the background. And the ISO data algorithm was our strategy how to determine the threshold. Yeah, so the task is determine the threshold for segmentation. And so we had this picture in mind that this could be the histogram of our image. Yeah, with two clear peaks, one for the background intensity, one for the foreground intensity, and that we wanted to put this threshold in the middle, and doing so without figuring out where these peaks are. And we characterized this as follows, namely that this threshold is supposed to be the mean value of the mean values in the different parts of the image. Yeah, so this area here is what we see in the histogram as this part. So it's integrating, taking the average here, so it will find roughly this position, and this will, the other part will find roughly that position. It's just a question how can we solve this nonlinear equation here for phi, and the idea was a fixed point iteration. So we called this phi of theta, and just iteratively apply phi over and over again. And we were wondering whether this converges. And what we have shown is that phi is increasing. Yeah, so that means phi of theta 1 is smaller equal phi of theta 2 for theta 1 smaller equal theta 2. Yeah, and we know that phi applied to the interval 0, 1 stays in the interval 0, 1. Yeah, so f has values in 0, 1, so both of these averages here will be between 0 and 1. So of course phi has to be as well, no matter what theta we in 0, 1 we put in there. So, and together these two things show the convergence. And why is that so? So we take now the theta 1, so any starting value. And now we have two cases. If theta 2, which is phi of theta 1, so this is either bigger equal to theta 1 or smaller equal or smaller to theta 1. And in this case here, we get that theta n plus 1 is theta n. Yeah, because we just apply theta on both sides to go to theta 2 and theta 3 here and so on. And since the theta is increasing, it will maintain this relation. So we have an increasing sequence. So theta n is increasing and bounded. Yeah, and an increasing bounded sequence of real numbers always converges. Yeah, that's one of the fundamental properties of the real numbers. Everybody familiar with this, the fact that these bounded sequences of real numbers converge? If not, feel free to speak up and I can try to illustrate. Yeah, so, okay. So, what is the situation? So, we have a bounded sequence, so that means there is some interval in which everything happens. Yeah, all of these things are inside this interval. Here we have 0, here we have 1. And now we put in our seeters. So we know it is increasing. That means we have like theta 1 here. I put the index on top. Theta 1 here, then theta 2 has to be right of it because it's increasing, and so on. Theta 3 has to be further right. So and we're going always further to the right. But we can never exceed 1 since it's bounded. So it means it has to converge to, so it has to stop at some point. Yeah, and probably not 1. We can stay strictly, yeah, we can end before. But since we must increase and we have an upper limit, there has to be convergence. Yeah, so this is like very important to have the real numbers because you can think of approximate pi by adding more and more digits. Yeah, so you would converge to the real number pi, but this would not converge in the rational numbers because, like, even though the limit is somewhere there, it's not in the rational numbers, but the real numbers are complete in this sense, so that's why we get this conversion. Yeah, and this also holds true for more than 1D, but in 1D the picture is very, very simple. Yeah, but so no, in one, but in more D it's more complicated because there you don't really have the notion of monotonicity because you can go in circles and yeah. So, but for real numbers it's always true. So that means in this case that we have this relation, we get our convergence, and now the second case is so the only thing that changes is that we have a smaller here, but now we can apply phi again. We have the monotonicity, so we just get that the sequence is decreasing. Yeah, it's just the picture is this way that we are going in that direction and somewhere stop above 0, but the argument is exactly the same. So that means our isodata algorithm will converge to some threshold that we can use. Of course, you can ask for a little more because our original goal was to have a fixed point. So that theta equals phi of theta. So far we just know that we get a limit theta, but we don't know whether the limit fulfills this condition. And we don't even know yet whether phi actually has a fixed point. And let me briefly comment on that. This will be done in one of the exercises. So what you can show is every monotonic function from 0, 1 to 0, 1 has a fixed point. Yeah, so fixed point means it's cutting the diagonal. Yeah, and your function phi, so you have to start somewhere in 0, 1. And you are monotonic, so you can never go beyond above 1. So at some point, you have to cross the diagonal. So even if you have jumps. Yeah, but this is a nice exercise to actually verify that this is fulfilled. And in case this phi is continuous, the limit is a fixed point. If it's not continuous, it does not have to be. Yeah, that's some case where we don't have guarantees, but at least we always know that we will converge to something that we can use. And one remark on how to actually compute this, because if you would use this formula to compute it, you would always have to compute these integrals or sum over, so determine these super and sub-level sets and sum over all the corresponding pixels. And there's a simpler or more efficient way to do this by using the histogram. And let me show you how that works. So the average gray values can be computed with a histogram. And computing this is also a nice exercise. So this mean value of f in the sublevel set for theta. So this is the first of our values that we need. We can compute with the histogram by integrating s times the characteristic function from -infinity to theta with respect to the histogram. And we have to normalize by the same term without the scaling by s. Yeah, so this is like the volume of the sublevel set, and this is the integration of f in that sublevel set. And yeah, these continuous formulas may look a little strange, but if you plug in what we learned for this push forward measure or image measure, this you should see why we have this relation. And so the same is true for the other set. We just need to adjust accordingly. So we have now f bigger theta here, and here we only have to consider values above theta. And I guess the discrete version of this integration will look more intuitive for you. So let me also write down that. And this is also what you would implement when you do this. So if f is now a discrete image, with value range 0 to n, so our typical finite number of values, then these complicated looking integrals are very simple sums. And we get that phi of theta is 1/2. So now we are summing from 0 to floor theta. And so this is the same as the as this integral. Yeah, it's like yeah, we're taking this histogram here, and like for every entry, we scale the number of times the value occurs by the value itself. Yeah, so this gives us the integration that we need. Yeah, so this is something you can easily compute from the histogram that you can pre-compute, and now the scaling is very similar. It's just without the s. That's exactly the same difference that we had here. Yeah, so there was with s and without s. And yeah, the other part works analogously. So I just need to change from where to where we are summing. Yeah, so we stopped at floor theta. So that means to get all the remaining gray values somewhere, we resume at floor theta plus 1 and go to the end of the value range. Yeah, and this is how you would implement the method. So you first compute the histogram, and then for every theta you evaluate these sums. Yeah, and this is only this is like only 1D operations because we are in the histogram space. For these to compute these integrals here, you would have to do 2D operations because you are in the image space. Okay, so that's all I wanted to tell about the point operators. So it's time to move on to more powerful operators that not only take into account one pixel value, but that can also make use of the local information in an image. Yeah. So what do the neighboring pixels do? Yeah, and these are the local operators. Yeah, and if you think back in the beginning, I said we start with these point operators, go to the local operators, and then continue further to the global ones. So we are like at stage 2 now. And to motivate what the structure of such a local operator is, I would like to introduce a very simple of those operators, which is called the moving average. And the task that this operator is intended to solve is denoising. Yeah, so we start with a noisy image. F, and the fact that it's noisy means that F is some F0 plus some noise term. Yeah, and F0 goes from RD to 0, 1. And is the image that we're looking for. Yeah, the image without noise. And N is the noise. And what we need to assume here for this to make sense is that the noise has mean 0. But this is usually a reasonable assumption for most kind of noise. And now we consider the following. MRF of X. And before I write this down, perhaps you can guess what this could be. Yeah, so it's called moving average. And now we want like a better value at the pixel X, in the sense that we want less noise in the pixel X. And what could we do perhaps? Yeah, exactly. So we would take a window around X, compute the average, and since this window is moving, this is called moving average. And this is exactly what is happening. And we can define this with the following notation. So we are taking the mean value of F inside the ball around X with radius R. Yeah, so the window in this case here would be a ball. Yeah, and let me define the ball so that we know this notation. So these are all points in RD where the distance, the Euclidean distance, is smaller, to X is smaller than R. Yeah, really just a ball with radius R where the boundary does not belong to the ball. So it's the open ball. Also, it doesn't matter here for the integration whether you include the boundary or not. Yeah, and this is pretty much the simplest denoising method. And this is called moving average. And I now realize that I completely forgot to show you what the isodata algorithm actually does on our Blackboard image. So nobody asked for it. But let me still switch back before we go on with this moving average. So this was our original Blackboard image. And here I did exactly this iteration with computing the histogram. And here is what we get. Yeah, so now we can see there's only black and white left. And the image is now much more readable. And for instance, if you wanted to do character recognition, which of course is pretty difficult with my handwriting, but at least it would get quite a bit simpler with this thresholding. If you pay very close attention, you can see that there's still some problems. For instance, you can't see the mouse, just point to it. Here, I had to erase while writing, so you can see some problems here, and it's probably a little bit too dark here. So this will be further improved later on, but overall, I think the chosen threshold is pretty good. I think you would not really be able to improve it more when you try to manually adjust the threshold. Okay, but I only realized that I forgot to show this because I wanted to show some examples of what this moving average looks like. Okay, so like continuously, it is very natural to take a true ball, but if you think more about the discrete world, it would be probably more natural to take a square or a rectangle because it's much easier to compute in your on your pixel grid. And yeah, let me also write down that. So instead of a ball in the Euclidean norm, yeah, which is just this 2 norm, we also consider other norms. For instance, infinity norm, because it's so easy to compute in the discrete case. Yeah, because our pixel grids allow us to represent squares easily. Yeah, and balls, one has to round to the pixels. Yeah, we take exactly the same definition here, except that I put an extra infinity here, which means that the norm is changed to the infinity norm. Yeah, so it's just always the maximum over the components. One thing I didn't mention is that usually we considered images on a rectangle, yeah, some omega. Here, I chose not to do so to avoid boundary effects. Yeah, because if you think about your moving window or your ball, you have to do something when you are close to the boundary, when your window is trying to look outside the domain. Yeah, and in order to avoid this, when looking at the first example, I just said there is no boundary because the image is living everywhere. But we will come to this, how to solve the boundary problem. Yeah, so now this is like a very simple idea that is useful to also consider all kinds of other kind of averaging. And not just the mean value in a certain area, but you can do all kind of weighted averages and even other things like derivatives. And for this, it is helpful if we rephrase this integral formulation to that we see better the structure, so that actually something is applied to this f. And we can use the characteristic function of the circle. So 1 inside the circle, 0 outside. This MRF can be written as the integral over all of RD, f of y, 1 divided by the volume of the ball times the characteristic function of the ball times at position y minus x. Yeah, so why is that the case? So this average just means we scale by the volume of the ball. That's this factor. Yeah, so the volume of the ball doesn't matter where the center of the ball is. If the radius is r, the volume is always the same. Yeah, that's why we can put it 0 here. So these correspond to each other. Now this limits the integration domain to the ball centered at x. So now we are integrating everywhere. So we're just putting zeros outside the ball. Yeah, so it would be immediately clear if we had the ball centered at x. Now I have the ball centered at 0, but we are just adjusting the argument here. So this here is mapping x to 0, so we only have this characteristic function. And this now can be slightly changed further by change of variables. Yeah, if I replace x or y by y minus x, this is f of x plus y. The scaling stays the same. And here we have a y instead of an x minus y. So everybody familiar with how to change variables in integrals with more than one dimension? If you're not saying no, I assume yes. Sorry? You're not? Yes, it's a substitution rule for multiple dimensions. So I put this into the appendix. Probably we just have a very brief look. Just to remind. Yeah, here. So this is essentially what the substitution rule looks like. Yeah, you have your change of variables, and you need to scale by the absolute value of the determinant of the Jacobian. And since this is just a shift, that is 1. Okay. Yeah, we will need this change of variables frequently, so that's why it would be good if you recall this. Yeah, and now this is a typical way to express a linear filter, namely that we have the image that we want to filter and multiply it by a kernel. Yes, this is our kernel. Now we see the structure, and this now leads to the following definition. We take a measurable phi, just a technical assumption. So be able to be able to write down the integral, I need to make some assumptions, namely that everything is measurable. But just think of this as filter and image. We have psi correlated with f. And I write this correlation with a 5 star. I hope it's distinguishable from the normal star, because we also have that sometimes. And this is just psi of y multiplied with f of x plus y dy. Yeah, so exactly what I had here with this being psi of y. And this is called cross correlation. Cross correlation of f and psi at position x. Yeah, and you can just think of this as moving your filter psi like to a position x, and then building the weighted average of your image with your filter. Yeah, and the easiest average would be just the mean, where everything gets the same weight and all weights add up to 1 or integrate to 1. Yeah, but this is the general structure. And now the operation of assigning an image f to the filtered version. So I am assigning the map f to a map that's mapping x to psi correlated with f at position x, is called linear filter with kernel psi. Let's see, should be some examples that I can show even before we look at the discrete version, as this is all still continuous. So on the left is the input. The bottom here shows the psi, and this here is now just a circle rounded to full pixels. That's why it's looking like a cross. And here the circle is getting bigger and bigger. And you can see that the image gets more and more blurry. Yeah, you can also see that the noise is reduced, but the price of this very simple averaging is that you lose all these sharp structures. And here an example where at least you hopefully see that there is a lot of noise on the left part, also with some stripes from the scanning process. Yeah, with the filtering, these effects are essentially all removed, but we lose some sharpness with this very simple approaches. And actually it will soon turn out that losing edges, so losing positions where the image intensity jumps, is a property of linear filters. That is unavoidable. So that is a drawback of linear filters. And we will actually prove that linear filters always have this behavior. Yeah. So they are nice and simple, and they have a lot of uses, but denoising is probably not the best use case for these filters, unless you have something very simple. Okay. Does this look familiar to anybody? Probably with a different sign here and a different name. Convolution, yes. So this is very, very similar to the convolution. Yeah, just the way how you interpret the filter is different. So with convolution, you would like mirror the filter at the origin, and with the cross correlation, you avoid this mirroring. But it essentially has the same properties, and that is what I want to look at next. Namely some properties of the cross correlation. Yeah, so to be able to properly work with the cross correlation mathematically, we need to figure out how it behaves and what we can do with it. And yeah, okay, at least one of these four theoretical things has also a very practical use. Yeah, so at first we want to figure out a little bit what properties this function has. So for instance, can we still integrate it? Yeah, so it's the integrate of this finite. Yeah, if we have some assumptions on the input. So that's what the first thing is doing. So we're taking numbers p, q, and r, all between 1 and infinity. And they have to fulfill a certain relation, namely that 1 over r plus 1 is the same as 1 over p plus 1 over q. And we have the convention that 1 over infinity is 0. Yeah, because so we are allowing the value infinity. So we have to say what's happening if we have 1 over infinity, and this is just meant to be 0. And if we now have f in LP, g in LQ, yeah, and here we need to pay attention that at least at the moment these two objects are defined on different domains. So this f I want everywhere, and for psi it's fine if I only know it somewhere. Yeah, for instance, this mean value filter for the circle, it would be fine if just omega is just a circle, just to keep things a little more general. And so if we have all that, then the correlation can be integrated with power r. So let's try to make a very simple example. Take r equal to infinity. So this is 0, and p and q equals to 2. That means we would have square integrals f and g. Then this says that this one is bounded, because here we would have L infinity. Yeah, which just means that it's an upper value for the pixel values. And we can say a little more. Yeah, so the fact that we are in this space just means that the norm in the space of this object is smaller than infinity, but we can further say how big the norm can be at most. It's just a product of the input norms. Yeah, so we have different powers everywhere, R, P, Q. But this is an important tool that allows us to bound this object, and only using properties of our inputs. And this equation is important enough to have a name, or at least its counterpart for the convolution. It's Young's convolution inequality. Yeah, if you replace the cross correlation with the convolution, you get exactly the same inequality. Some more rather simple things. So let's say that also our f is given on all of Rd. Then we have that the correlation of f with g at position x is g correlated with f at position minus x. Yeah, so we can flip the order, but oh, yeah, right. Yeah, this is wrong. Yeah, yeah, yeah. Yes. Good catch. Yeah. Yeah, in the proof we would have, we will see why there must be an RD. So it's not, omega is not, yeah. Yeah, so this, yeah, good catch. So this fit exactly to these conditions. Yeah, but if omega is equal to RD, then we can switch the roles of both arguments since the conditions are fulfilled. That's why it's making sense to look at the other order. And the price for changing is flipping the sign of the argument. And that's different to the convolution. For the convolution, the argument would stay the same if you flip. Yeah, and we can again say a little more, namely that the norm stays the same. Okay, so this tells us about like boundedness of the correlation, yeah, in which norm we can still bound it and how we can integrate. Now let's have a look at derivatives. So I assume now that psi is k times continuously differentiable and it has compact support. So that means that the set where psi is not 0 is bounded and closed. No, bounded is enough because we look at the closure. Sorry? No, it's just 0 in a bounded area. No, it's just non-zero in a bounded area. So we know that we only have to like look at psi in a certain range. For instance, our yeah, here it would be the circle with radius r where our support is, and we assume that the set where the function is non-zero is bounded. And we take f in LP with NEP between 1 and infinity. Then the correlation of f and psi is also differentiable. Yeah, so this the correlation inherits the differentiability of its arguments. Yeah, so it's sufficient if one of those is differentiable for the result to be differentiable. And we can also say what the derivatives are. So if alpha is a multi-index with absolute value smaller or equal to k, so alpha is just a vector of natural numbers, including 0, and the sum of these numbers is supposed to be smaller than k. Then we have that the partial derivative with respect to x to the alpha of the correlation is the same as f correlated with the partial derivative of the kernel. So everybody familiar with this multi-index notation? So this is like a vector of natural numbers, including 0, that says how often you have to derive in which coordinate direction. Yeah, so if alpha would be 2, 1, and we are in 2D, that means 2 times with x direction, 1 times with y direction. It's just a very compact way to write down derivatives of order at most k. And yeah, so the nice thing is you just need to compute the derivative of your kernel. to get the derivative of the correlated object. So if you need like a differentiable approximation of your image, which we at some points we will need, for instance, for edge detection or edge enhancement, this is a good tool. We will come back to that. And if omega is RD, then we can flip the order. Also, psi convolved with F is differentiable, correlated with F. And it's slightly different. So again, we just have to derive the kernel and correlate with the image, but we get a factor of -1 for each derivative. Yeah, that's why we have the absolute value here. Like iterating this -1 here is the chain rule. So, and yeah. It is, so I assume strong differentiability in the beginning. So I start with strong or classical differentiability, and the result is still strongly differentiable. So F is still just an LLP function. So this already tells you that the correlation really makes this smooth. Yeah, so no matter if F is looking very ugly, has many jumps, it's just really integrable. After the correlation, it's as smooth as the kernel that you had. Yeah, so it's you can even look at it as a limitation of this technique. Yeah, but so we don't need to go to weak derivatives here because we actually get strong derivatives. Yeah, and finally, some approximation technique which we will be using. So we take a kernel psi that can be integrated. We want it to be non-negative. And integrate to 1. So it has mass 1 and is non-negative. Moreover, for epsilon bigger than 0, we look at psi epsilon, which is a scaled version of psi. Yeah, so we are concentrating psi at 0 by scaling with 1 over epsilon, and this 1 over epsilon to the d is just the necessary volume change. So you can think of it like this. This could be our psi, yeah, non-negative, and let's assume that the area here is 1. What this epsilon does, like it concentrates the psi at 0, so it's getting smaller and smaller and higher. Yeah, and the scale here is such that the mass stays 1. So what do we do this or need this for? We also take an F, an L infinity, so something that is bounded. And if F is continuous at one position x, now a more technical argument, we have the following. And here's also something that you can like try to guess what this is, so I'm taking my f and I'm now correlating it with these kind of kernels that get smaller and smaller support and that are like higher and higher, and this limit epsilon to 0. So it really, when it collapses to 1 point, what do you would you expect to be the result of this limit? Yeah, so we are correlating f now with something that is very concentrated around 0 and that has mass 1. F, why 0? Because it's, yeah, but let's recall this. We have this shift here. So here we put an x. So, and this is like centered at 0. So we have zeros here, but we are shifting to update your guess. No. So this f of 0 was almost correct. It's f of x. So because we are like averaging in a very narrow region that's getting smaller and smaller, this actually converges to our original value. Yeah, if f is at least, if there's some continuity at this point, x. And so this is a tool that helps us approximating images. So this is only for theoretical purposes, because the nice thing is, yeah, we just here need boundedness, and we know from, for instance, from this part here before, if psi is differentiable, then this is also differentiable. So this gives us a way to approximate any function with differentiable functions. Yeah, and these kind of approximation tools are very important for proving numerous properties, because it's like often easier to prove something for a differentiable function and then show that it also holds in the limit. Yeah, because with the differentiable function you have much more structure. Yeah, and this is the tool for like showing properties for the limit. So, and f is uniformly continuous. So if f is uniformly continuous, then this is even stronger. Then this correlation converges to f on each compact subset uniformly. Okay, so a bunch of statements, and let's see. I hope we can at least prove first one. Let's see. Yeah, we want to prove now that this correlation can still be integrated, which essentially means that we need to check this kind of inequality. Yeah, so we somehow need to start on the left-hand side and try to estimate from above without exceeding these things that we can control. And yeah, that is our first task now. And this is also good to recall some important properties of integration that are often used in these kind of proofs. So let's take x in Rd and R equal to infinity. Yeah, so we can't prove the entire thing in its full generality in one go. Yeah, so we need to look at some cases, and we had this interplay of P, Q, and R. Yeah, and by choosing R to infinity, this is essentially a 0, and we can concentrate on the interplay of P and Q here. That's why we start like this. Okay. And yeah, so now first tool that we need to use is Hölder's inequality. who knows Hölder's inequality? So you did not read the appendix. Who knows Cauchy-Schwarz inequality? Essentially, and in more general. But who knows Cauchy-Schwarz? That hopefully everybody. So that the scalar product can be estimated by the norm of the individual vectors. Yeah, and the fact that this also holds for integrals is like a special case of Hölder's inequality. It says that like the scalar product of the functions can be bounded by the product of the norms, but not only the two norms like in the Cauchy-Schwarz case, but like the P and Q pair. Let me jump to the appendix so they can show this. What did I say? B7? Yeah. Yeah, so this is essentially the scalar product of the functions f and g, and we estimate by the product of the norms. But this not only works if like we have 2 and 2, because if you have 2 and 2, 1/2 plus 1/2 is 1, so it's fulfilled. But it's also working in more general cases. Yeah, so it gives us like a more flexible version of Cauchy-Schwarz for integrals. Yeah, so that's B5. And that is, yeah, Hölder is really an important inequality one should try to memorize. So first we just plug in the definition of the cross correlation and estimate by moving the absolute value inside the integral. Yeah, so without the absolute value here, it would just be the definition of the correlation. And I can estimate an integral from above if I integrate over the absolute value. Like triangle inequality for integration. Yeah, and now I have the product of two functions. The product of the function f and the product of the function g, which is shifted by x. So this is a case where we can use Hölder. Again, Hölder has the product of two functions. Here, this formulation is a nicer one, perhaps. So we can split it like this. So that means for this part, we get the LP norm of f, and here we get the LQ norm of the shifted g. Yeah, so this dot notation means that here is where the variable of the function goes. Yeah, I'm just adding this x here. And so this we can further estimate from above by the LQ norm of g on all of Rd. Yeah, so here we are just integrating on the subset omega, and we just make the integral bigger if we integrate over everything. And as soon as we integrate over everything, it doesn't matter anymore if we shift the function or not. Yeah, because we are integrating everywhere anyway. Okay, so that means we have estimated the correlation at a position x by the product of f and g in the corresponding LP and LQ norm. So, and this is completely independent of x on the right-hand side. Yeah? So there's no x anymore. So I can take the supremum over all the x. Then the left-hand side changes to the L infinity norm. Yeah, so the L infinity norm is just the essential supremum over this. And the right-hand side, since it doesn't depend on x, stays the same. Yeah, and that means we have shown this here for the special case that R is equal to infinity. Yeah, so at least one of our part of our claim is is shown. Now we consider that R is equal to P. Which implies that Q is 1. Why is that the case? For this, we have to look back. So if R and P are the same, we can just remove those and see that 1 is equal to 1 over Q. So Q has to be 1 in the case R is equal to P. And for P equal infinity, we have R equal infinity, and this we already covered. Yeah, so the case R equal infinity, we already have confirmed. So that means we need to look at only the case that P is smaller than infinity. And again, I will start with this. And what we do is we integrate the P's power. Yeah, I take both sides to the P and integrate. So that means that the correlation of f and g of x to the P dx is smaller or equal to the integral to the D. Yeah, I don't want to write that again. To the P. Yeah, the P's power is monotonic, so we keep the inequality, and integration is also monotonic, so we keep this here. And so this is something that we will use some more times. And now we first check the case P equal 1 and then P bigger than 1. And here we need another tool that, yeah, I think you should know, but probably perhaps not by this name. Who knows Fubini theorem? This essentially tells you that if you integrate with different with respect to different variables, you can change the order. So let me apply that, and then we can look how it is defined. So you hopefully see that it is something that you have seen before, but probably just in a different formulation. Because most of the time you actually compute an integral with more than one variable, you make use of it because you can then successively integrate with respect to the variables. And also decide in which order you integrate. So here it's just a little more complicated. So this equality is just like the definition of the L1 norm. Yeah, L1 norm just says we integrate the absolute value. Nothing special. But now this object is again here. We have chosen P equal to 1, so we can use this estimate from above. But now I already make a few changes. So P is I think there's actually a typo. I know. No, we don't need the absolute value. So P is 1. So these brackets are actually not there. And I can just change the order in which I'm integrating. So I'm first integrating with respect to omega now. So first, the inner is dx and outer then is dy. So I'm flipping those. And inside there, I'm taking out the f of y from the x integral. No, that's the wrong order of integration. Yeah, and I changed the order because this term here does not depend on x, so it allows me to remove this from the inner integral. And the nice thing about that, why the reordering helps, is that this here is just the L1 norm of G. Yeah, because we're integrating over all of RD, so the shift here doesn't matter. Yeah, same trick as before. But now the norm of G does not depend on the y. That's why we can take it out of this y integral. And what remains inside the integral is just the absolute value of f to be integrated, which is again the one norm. So the entire thing thus is the L1 norm of f times the L1 norm of G. That means we have proven the inequality for the special case P equals to 1 and R equals to P. So now we move on to the remaining part, which is P between 1 and infinity. And we now take P star, so that 1 over P plus 1 over P star is 1. Yeah, so this P and P star would be now something where I can use Hölder because it's a pair for how we can apply the Hölder norm, the Hölder inequality. Yeah, there I called it Q, but Q is already used in our formulation. That's why I call this P star here. And again, I will start with this object. The estimate from above. Exactly with this star. Just some slight modifications. So we have RD here, we have omega, that's all the same. F of y, G of x plus y, but now I'm changing a little bit. This is 1 over P, and G of x plus y, 1 over P star. Yeah, so this is just G to the 1 that we have here, and I split this in G to the 1 over P and 1 over P star. Since they're adding to 1, it's the same. But now, having it split like that allows me to apply Hölder's inequality. So just inside, yeah, on this inner integral. So the first one then is Fy to the P G of x plus y to the P divided by P. So this cancels. And then to the P divided by P. Yeah, so Hölder says I have to take the P's power here. Gives me a P here and 1 here. And outside I have to take 1 over Q, 1 over P. Combined with this to the P, we have this P divided by P. And the second part here now is with P star. G of x plus y dy P divided by P star. Yeah, Hölder again has here P star divided, adds to the P star, which cancels with the P star that I already have. And the P that I have here is combined with this 1 over P star there. And then again, I can use Fubini to reorder the integrals. First realizing that this here is smaller equal than the LP norm of G to the P divided by P star. Yeah, so that means this integral here I can take out. And on the rest, I apply Fubini. Yeah, I get my Fy to the P. Yeah, here's the 1. This is transferred. And we have this integral over Rd, G of x plus y dy. No, dx dy. I changed the order. And I still have this. And here again, this is G in the L1 norm. I know it's tiny bit too large. Only here. So this inner integral is again just the L1 norm. And what remains is the AP norm of f to the p. And g in the L1 norm. And now we have 1 plus p divided by p star. Yeah, because we have p divided by p star here, or here, and here's another 1 that has to be added because it's a product. And finally, we take the p's root. So p's root outside here gives me the LP norm, and the p's root here is p divided by p, so we have 1 here. And here we have then 1 over p plus 1 over p star. That's also 1. So that's exactly what I was claiming. Okay, and then we are also done with the time. Let me make a final remark, and then we are done for today. So the case R not equal to P can be done similarly, but I don't want to go even further into this. I think this here already shows a lot of examples how these integration tricks works and how you can estimate. And in case somebody is really interested in this, I put a reference to the book of Lieb and Loss, but we won't need it in this generality. But the final case here, R not equal to P is in there. And yeah, so next time we will then continue with the other statements. Yeah, thanks for your attention.